Hello, Physics 30. So today we are moving on to lesson 4 of chapter 12. So the first thing we're going to learn is about something called a velocity selector. Okay, a velocity selector is basically where we have a magnetic and an electric field acting on a charged particle. And we're looking for balanced forces. The reason we're looking for balanced forces is that we want to pick the right velocity. So if we have this equation here, it looks like this, right? So we have the force magnetic and the force electric are both going to equal each other. We do this, we can cross the Q's out, which leaves us with VB equals E. So by choosing the magnetic field and choosing the electric field, we can then decide which velocity of particles we want. The problem with that is whenever we're creating particles or charged particles and we're sending them out from usually what's called an electron gun or an ion gun, they come out at many different speeds, right? Many different speeds. So we're going to pass them through this velocity selector, which is again just a magnetic field and electric field overlapping each other, which allows us to choose which velocity we have. Then once we know the velocity, we can use that in the next part, which we'll see at the end of this lesson. All right. So I've filled in some notes for you guys already. All right, and this is kind of an idea. We have magnetic field, electric field, an ionic accelerator. Okay, it's also known as sometimes an ionic gun. So what's going to happen here is we're going to shoot 3 objects through, right? The first one being 3 of the same objects but different velocities, and the second one being D and Q. So first we're going to look at Q. So Q, right, bent downwards, right? So these are positive ions, which means that the magnetic field was stronger than the electric field. Since the magnetic field was stronger than the electric field, it was actually probably going too fast. All right. For P, it got bent the other way. These are positive ions. So what's happening is that the magnetic field is not as strong as the electric field, right? So the electric field's winning, and that's telling you Fe is larger, which means it was going too slow, right? Too slow. All right, and then we of course get D, right, which is going to go straight through undeflected because the forces are going to equal each other and cancel each other out. Since these forces equal each other and cancel each other out, we're going to be just fine with understanding that. Now, does this do for us? Why do we do this? Well, now without being able to tell, because you can't take a radar detector and measure the velocity of an electron, right? What this does is this basically is a velocity selector. Now we know V. Now we know V. That's right. So as it enters this area, we know what the velocity is. Since we know the velocity, now we can do the next level of physics, right? Okay. So this question kind of looks like this, right? We have a beam of singly ionized hydrogen ions. It is not deflected as it passes through velocity selector. Okay. It passes having a magnetic field strength of 1.8 times m to the t to an electric field of 500 . Okay, draw free body diagram. So as the hydrogen ion passes through, right, we are going to have a force down and a force up. One is force magnetic and one is force electric. Okay, what you'll notice about these is that the charge doesn't matter. It doesn't matter if it's 1 charge, or 2 charges, or 3 charges, or however many. It doesn't matter. So we're going to actually cancel it out. Right, and as you guys see, I've already kind of filled the notes out a little bit just to help you out along the way, help make my videos a little bit shorter. Sorry, I'm having a little trouble with my nose a little stuffed. Okay, so we're going to cancel those out, and we're going to left with this, and we're determining the speed. So V equals, zoom in so my writing's a little neater. E, don't forget the arrow on the E, you guys, because we have to note that this is not energy. E over B, so V equals 500 divided by 1.8 times 10 to the 3. We're going to expect large numbers because these are small particles moving at very high speeds. And we're going to get the velocity is equal to, how many sig digs we want here, guys? We want 2 sig digs. 2.8 times 10 to the 5 meters per second. All right, so pretty fast. But now we know that everything that makes it out that final hole, again, we are going to have a hole there, and anything that makes it through that hole is going to be going exactly that speed. If it's going faster or slower, it will hit the wall and not go that speed. So we know the V after it passes through that hole. That's why this velocity selector is super important. All right, so there's the whole question there. Again, if you need to pause the video to write it all down, go right ahead. All right, I'm hoping to find this thing here so I can show you guys this. I'll try and share it with you. But what's interesting is, so now previous one is velocity selector. We have magnetic and electric field acting together. What happens when we have just a magnetic field? Well, you guys should have already read this. When a charged particle's velocity is traveled parallel, right? So it's parallel to the magnetic field. The magnetic field does nothing because we know that V and B have to be perpendicular. What we actually notice is that if it goes in perpendicular, it will get deflected. But the thing is it got deflected just like it would in gravity, right? So if we have a particle getting deflected in gravity, it would start to do this, right? Okay. All right. And what we do is if we zoom out, and it can keep doing that, right? It's getting deflected, getting deflected, getting deflected. It's going to keep getting deflected because it's not going to hit the ground. And what we're going to get is a circular path. The same as how we had the Earth and we were orbiting and we were moving fast enough, we would orbit around the Earth in a circular path, right? Same idea here. We have the force acting radially inward, right? So the force, which I'll draw in green here, the force is always to the center. So this is where you guys should be going, oh no, we're doing something. So what am I now bringing in here? So now I've got a force magnetic that's acting radially inward. I've got a constant inward, a constant velocity. This is going to tell me that somehow we're going to have force magnetic related to force centripetal, right? We're meeting all of the circumstances for centripetal motion. So this is where I should hear cheering. You guys are excited, right? We're excited for about centripetal motion coming back. So we can do that, and we can look at this. Again, I can't show this video great. I'll see what I can find here, okay? So when a charged particle enters a region that has a magnetic field, they'll be deflected into a circular path. Since we know it's a circular path, then we can, if it's only force, then we can do this, right? And so what's nice about this is that we can cancel out some V's here, right? This V and this V and the V squared will always cancel out. This V and this V squared all cancel out. And it leaves me with this equation here. QB equals mv over r. All right. So what's nice about this is with our velocity selector, we're probably going to know the velocity. We can always pick the magnetic field. The charge can be found, and then we can measure the radius. If we can do these four things, we can then work back and find mass, stuff like that. Or if we know mass, we can find charge. Or we can, if we know the mass and the charge, we can find the radius. If we know the velocity, right? So there's lots of little things in here where we can kind of pick and choose what we need, and it can give us 5 different variables of little particles. Remember, we can't see these particles, right? We can't see these particles, and we can't weigh them. Since we can't see them or weigh them, then we're going to have to think of creative physics methods that allow us to cause this to all happen, right? Okay, that allow us to figure these things out without being able to see them or measure them, because we're learning that atomic physics is kind of the backbone for what's actually happening, right? It's kind of leading us into why is gravity acting the way it acts? Why do the strong and weak nuclear forces act the way they are? What's actually happening? How do magnets work? Like all these things come back to atomic physics or very, very small physics. And we're working into things even farther and smaller in like string theory, right? And we can't understand them if we don't have a way to measure devices, okay, without being able to see things. All right, so this is going to combine basically these 4 equations, right? Remember, we have to find velocity of these things depending on what's going on, okay, and working backwards through this. All right, and this is going to be focused primarily on physics principle number 2. All right, so since we have physics principle number 2, it's uniform circular motion, where the F net is radially inward. All right, so what we're going to notice here is an electron approaches an electric field, and a magnetic field is shown in the 2 diagrams below. Okay, so we're going to see, just take a look at this. Describe the direction of the electron's motion in each field. All right, so an electric field, what we have is that if the electric field's aiming down, that's the way a positive would go. So a positive would go towards a negative, and like this. So our electron is going to come in, and the force is always going to be up. So our electron's kind of going to follow that path, just like parabolic motion, right? Now I've got a magnetic field, right? The magnetic field is directed downwards, so I'm going to use an electron. This is where we bring in our left hand, right? Left hand. Electron's the thumb, going to the right, magnetic field aiming downwards. Okay, and so which way is the electron going to go? Well, it's going to come out of the page, but in a circular motion. So out of page, but in a circle. So it's kind of going to get deflected out of the page, then it's going to loop and be pushed back into the page, and then out of the page, and so it's going to kind of basically loop in and out of the page. Again, I'm just checking to make sure I'm doing that right. Yeah, left hand, palm should be up, so the force is originally out of the page. But then once the electron gets to the point where it's going to be going up, then the force is to the left. Then the electron moves more and the force changes, okay? One way to do it is just go back to this page here, all right? Check out this example right here. Okay, and use your third hand law to kind of understand what's going on here, right? This electron, why is it going to go in a circle? Okay, and just do it at different spots. So use your right hand here, 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 and here, and here, right? Use your left hand, but third rule, and discover where this all goes, okay? Make sure you get that understood. All right, this is why we have circular paths. All right, so I was just going to give these notes back to you in case you haven't written them down. All right. So what I've got here is if electrons accelerated across a field, then they leave the electric field and enter a magnetic field, causing them to turn in a circle. The path of the electrons is shown. Use labels to indicate the direction of it. So we have starting from rest, and that's accelerated. So there's acceleration happening here, right? So in order for the electron to be accelerated, this must be positive, and this must be negative. So then which way is the electric field? Well, the electric field is actually that way, right? Okay, which way is the electric force, though? Force electric is this way, right? Now we got to figure out the magnetic field. We use our left hand, and we just think about which way the force is initially, right? So initially, the force is this way, then this way, and then this way, right? So initially the force is downward, so our palm should be facing down, right? Down to the bottom of the page, and our thumb should be facing to the right of the page. So palm down, thumb to the right, and you're going to notice that the magnetic field, whichever, if you do position 1, position 2, or position 3, the magnetic field is going to be pointing into the page. Magnetic field is going to be into the page. All right, which we just denote with a bunch of X's. You can put a circle around them or not, it doesn't really matter, but put them into this page. All right, the magnetic force acting on the electron is going to be considered radially inward, right? So the force magnetic is radially inward. I'm pretty sure I just spelled that wrong, but you guys know what I mean. So the force magnetic is radially inward. All right, so then we can start applying things. So this question has a singularly charged particle enters a 0.410 Tesla magnetic field at 8.1 times 10 to the 5 meters per second. The velocity and direction of the magnetic fields are perpendicular to each other, which is important to know because now we know there's going to be magnetic force. Determine the particle's mass if it turns in a circle having a radius of 0.680 meters as it travels through the magnetic field. So I've already done this question before, you guys, just to speed things up a little bit, all right? So I wrote down my variables that I know. What are my variables that I know? And then I started with force magnetic equals force centripetal. Because there's only one force, and that's the magnetic force, and it's going to pass through or cause a centripetal motion. So remember before in physics 20 we learned that centripetal motion was caused by friction or by a tension or by gravity, right? This is now a new way. It can be caused by magnetic force, okay? So I'm going to solve the equations, right? Pull them off my formula sheet and solve them like I normally would. Get rid of the v cancels the v squared, and then just multiply by r and divide by v, which gives me this mass of 5.5 times 10 to the negative 26 kilograms, all right? So that's how we solve this problem, and we go from there. Again, if you want me, I'll just zoom out. Okay, again, notice that it says singly charged. That means the charge has got 1.6 times 10 to the negative 19. So it doesn't say 19, great, but it says it down here. Okay, 1.6 times 10 to the 19. All right, so what we're leading to now is something called a mass spectrometer. All right, so a mass spectrometer basically allows us to discover the mass of an object using this, which is good because we have things we predict, right? But in physics, if we're going to predict something, we need to prove it. In order to prove it, you have to know the particle's mass, right? So there's a whole thing where they're going to go through this process where you have ions, they all the same kinetic energy, push them through there, and then we do this magnetic field, and depending on their velocity, we're going to get different masses and different mass. So if it's a heavier object, it will probably go like so. If it's a lighter object, it'll go in the inside path. So the heavier the object, the more momentum it has, and it'll go like that. Yeah, I think it's going to work like that. My brain's not on, right? So the idea is that by using this, we're going to cause a different amount of deflection and stuff like that. Of course, we have an acceleration area, and we go from there. Okay, so let's look at one of these mass spectrometers kind of built up. So a simplified mass spectrometer consists of 3 parts. The accelerator, so we got to get the particles to a certain velocity. The velocity selector and separator. And then we're going to label, identify the parts indicated. So we're going to start part 1 here. Okay, part 1, the accelerator. So the accelerator part, okay. Don't try and do this all at once. Break it down to the 3 sections. So the accelerator part, what we should notice is that we have this positive and negative here. So we're going to make sure that's negative. This one is negative, and this is positive. All right. So what is the charge on the particles? Well, if it's accelerating, right? It's accelerating, the particle must be positive. All right, the particle is positive. So then what's the direction of the electric field? Well, the electric field is going to be this way, right? It's going to be to the right. All right, so that's the accelerator. So it's going to speed them up. Then we're going to have a velocity selector. So first thing you should note, then this is something I missed when I first noticed this, is that it tells us the direction of the electric field, right? It tells us the direction of the electric field, so it's like so, which means that what is the direction of the magnetic force? Or the direction of the force electric? Then the magnetic force must be acting upwards, right? That will cause it to have basically a different idea. All right, so we have the force electric is acting downwards, so the force magnetic must be acting upwards. All right, so the force magnetic must be acting upwards. Okay, so now we're going to see the charge of the plates, right? So we know the particle itself is positive, and if it's the force electric's down, then it'd be negative plate at the bottom and a positive plate at the top. So the top plate is positive, so it's pushing it down, and the bottom plate is negative. All right, that's good. Okay, so now, we're charging the plates, positive on top, negative. So we did this one. This is good. All right, so those are done. All right, so number 3, the direction of the magnetic field inside the wire loop. So remember, if we have electrons passing through a wire, it does create a magnetic field. So what we're going to do here is we're going to think, okay, the force is up, so we're going to use our right hand because we have a positive particle. The force is up, and the motion of the particles is to the right. Okay, so thumb to the right, palms painting the top of the page. It's kind of hard to do with your arm, which tells you that your fingertips or the magnetic field is into the page. So the direction of the magnetic field is into the page. Right, we can just denote that with a little bit of X's here. All right, so then we've got this idea here, where we're going to go ahead and it's going to pass through, and we're going to go to section 3. Right, so section 3 is a separator. The separator is then going to be just a magnetic field. It's the direction of the magnetic force. The magnetic force Initially it's upwards, then here, then like this. But it's initially upwards, right? So initially, the magnetic force initially is upwards. So then what is the direction of the magnetic field? Well, we have a right hand, palm is going like this, the magnetic force is still up, so then the magnetic field is into the page, right? So to keep in mind that there is a subtle difference here. We have a magnetic field here into the page, and a magnetic field here into the page. This first magnetic field in the velocity selector, all it's doing is trying to keep the electric field from winning. It's keeping them straight. Okay, so it's not going to be circular motion because we have two forces acting. We have both magnetic force and electric force. Okay, that's not going to result in circular motion. When we get over here, right, we are going to get circular motion because now the magnetic force is the only force, and this is where that Fm equals Fc comes into play, right? So over here, Fm equals Fc. Over here, Fm is just trying to cancel out force electric, right? So keep that in mind, that there is two different forces in magnetic fields. They can be the same direction, but they're not always going to result in the same path. Depends if they're the only force or if they're multiple forces, okay? Okay, so these synchrotrons are super cool. They're particle accelerators. So a particle accelerator is something that basically gets particles very in circular motions using magnetic fields and try and get them as close to the speed of light as possible, all right? On the back of your formula sheet, this the speed of light. It's 3 times 10 to the 8 meters per second, all right? And so what's awesome is that we have basically one in Saskatoon that basically can get electrons up to 99.99985% of the speed of light, and a ring that stores them has a fast electrons with a radius of 27.2 meters, okay? So there is something we need to know about particles in general, is the faster you accelerate a particle, it actually gains mass. I know it doesn't sound right, but it does gain mass. So an electron normally it has a mass of 9.11 times 10 to the negative 31 kilograms. What actually happens is when we're moving this fast, the electrons will actually become heavier. It's a very complicated physical principle that has to do with relativity and Einstein and all this stuff, and it's over my head. But just know that when something's moving very fast near the speed of light, it actually starts to gain energy instead of mass, or starts to gain mass instead of speed. We're adding energy, it gains mass instead of speed, which is very interesting, okay? So what we're going to do here is we're going to use these ideas, all right, and we're going to figure out what is the magnetic field strength that you need, right? So first of all, we're in the storage ring. Okay, the storage ring is 27.2 meters. So I don't noted that here. The mass, the relative mass, all right, is there. Okay, the velocity. This is the speed of light. I know it's not 99.99%. It's still going to round to 3 times 10 to the 8, and it's an electron, so we know its charge is this number here. So the speed and the charge comes from us reading and knowing it's an electron or knowing that it's near the speed of light. Okay, it doesn't say anything about electric field, so we're going to start with Fm equals Fc, the same as we did before. Solve. These cancel the V, right, as we have done, cancel the V, and isolate B, right, isolate B. And when we do that, we put the numbers in. Again, I'm gonna have the odd number wrong on here, you guys. I've double checked them, but I always make mistakes. You know that. Let me know. Okay, and B is gonna equal 0.468 Tesla. Okay, so there's quite a bit of stuff going on. Take a second, pause the video, double check my math, all that kind of stuff. All right, so that's gonna bring us to the end of this lesson, you guys. Okay, you should try practice problems 11 to 18. When you finish practice problems 11 to 18, you are prepared to write that little mini quiz I sent. It's got 5 questions. Write it on a piece of paper, or try on the computer. It'll take a long time. Write on a piece of paper and send it to me via Google Classroom. The assignment is already up. Okay, then do your next 10-foot anticipation guide. I am going to say this again. I want you guys to type your anticipation guide out, all right, into the computer, because I am going to use that as something to mark you on. I'll be very generous, but I am going to mark you guys on those questions, okay? You should be getting lesson 5 sometime next week. Good luck, you guys. Remember, let me know if you have any questions.